give a talk in this conference. When I had invitation, I realized this is one of the main focus of the conference, is that I have seen a lot of talks about neutrino physics. Huh? Then, as you can see, I will talk about probing the nature of neutrinos with new forces. So, before I start, I would like to say that this presentation is based on my collaboration with some of my students that are in California, postdocs, that are here in California, and one of my collaborators that is in California as well. Then, in particle physics, we have been thinking about the neutrino mass, how neutrino mass are generated for a long time, and still we have no clue how how they get mass. We have many ideas, but when you think about all the ideas that we have in the field, the truth is that it's actually very, very hard to test. And then I will talk about different ideas that we have for neutrino masses, and something that is very, very important is how to test these ideas, because we want to understand the complete the idea of how to generate masses for all the fermions in the standard model of particle physics. But then, in the case of the neutrino, can be really, really challenging, because the relevant scale for the mechanism behind neutrino mass can be actually coming from the higher scale. If this is the case, there is no really hope. Apart from that, we know that neutrinos, they can be Majorana fermions. In this case, you have effective violation B minus L in 2 units, or they can have a second personality. They can be Dirac fermions. Huh? In this case, the B minus L symmetry is conserved. And these are the main possibilities that we have for neutrinos. Clearly, I saw many talks about neutrinos of beta decay, which is something very, very important from the experimental point of view to really establish the nature of neutrinos. From the theoretical point of view, we have to really understand all the possibilities and see, combining all the experiments, how we can test the different ideas, okay? Then let me talk about the case of Majorana neutrinos. Huh? As we know, neutrinos, they can be Majorana fermions. And in this case, we have a lot of ideas to generate neutrino masses, okay? I am having, okay, we have a lot of ideas to generate Majorana neutrino masses, from the type 1 seesaw mechanism to, the Witten model, and many, many ideas like this, okay? All these ideas are really toy models. These are not complete theories, because what I mean by complete theory is that you need a theory where you can really predict the neutrino masses. At least the relevant scale can be connected to other scale. And this could allow us to really test the origin of neutrino masses in the case of the Majorana case, okay? But we can actually implement all these toy mechanisms in different theories and see how we can actually test. Huh? But these are, there are a lot of ideas for Majorana neutrino masses, to generate Majorana masses, but we have no really clue which one is the one that will play a role in nature, because still we didn't discover that. Then, as you know, the simple canonical seesaw, type 1 seesaw mechanism, where you just have a Majorana mass for right-handed neutrinos and the Dirac term. This is a toy model for generated neutrino masses, where the only thing that we know is that the mass matrix for neutrinos is suppressed by some scale, and proportional to some MD scale, that typically, if you assume that this scale MD is around the letter W scale, we know that the canonical seesaw scale can be very, very high, around close to the grand unified scale. And this is, many people like in the field, the connection of to grand unified theory. But the truth is that we don't have any experiments that can allow us to have access to these scales. If this is the case, if this is, for example, the mechanism behind neutrino masses, we are really, in trouble because, we discovered the standard model Higgs, and we understand how generate masses to most of the fermions. Still, we didn't measure the coupling to the electrons and things like that. But at least we expect that all the charged fermions, they are getting mass in the same mechanism, and we know how that is playing a role in nature because the Higgs will discover. If the neutrino mass is generated at the super high scale, clearly there is no hope. No? Now, the simplest way to to connect this mass scale to a new physical scale where it's symmetry breaking and not putting by hand the symmetry, the mass scale for right-hand neutrino, is to consider theories where you have a local B minus cell. It is very well known that once you have the right-hand neutrinos in the theory, you can actually cancel all the anomalies and make B minus cell a local symmetry and study the spontaneous breaking B minus cell. In this case, the only thing that you can do is to relate the right-hand neutrino masses to a new scale, symmetry breaking scale associated to the breaking, the spontaneous breaking local B minus cell. And then, in this case, as I said, you just need to break in 2 units local B minus cell. And the nice thing about this theory is that we like gauge theories. The standard model of particle physics is a gauge theory that works. It's a fantastic gauge theory. And if we follow the idea behind the standard model, we know that U1 B minus cell is the simplest theory local, with a local gauge symmetry that allows us to understand the original neutrino masses in this way. Clearly, there is a problem here when you try to understand a simple gauge theory, is that this particular theory doesn't really predict if the neutrinos are Majorana or Dirac, because I am putting by hand a Higgs that has 2 units of B minus cell to generate the Majorana mass of right-hand neutrino. So easily I could break this symmetry in a different unit, larger than 2, or many different possibilities. I could have Dirac neutrinos. And therefore, the theory, even the minimal theory, fails completely to predict Majorana or Dirac neutrinos. Doesn't really make a hard prediction regarding that. When I say always prediction, is for me, it's very important to take the simple theories that you can write down and show if there is a prediction coming from this theory generically in the minimal theory. If no, it's really hard to make any statement. Okay, but at least here I can connect the new scale to a symmetry breaking scale connected to B minus cell and do the usual system. And then again, when you ask the same question, what is the B minus cell scale? The scale can be huge. There is no way really to test this in any experiment, okay? And you get very depressed because it's actually really, really hard to imagine you can test this theory. What happens when you try to implement the same ideas using theories like Patis-Alan or grand unified theories is that typically in that, like in grand unified theory, the Yukawa-Dirac is actually connected to the mass of the quartz. And in this case, it's even worse. There is not even a freedom to have a lower scale CISO, generically speaking, the simplest mechanism. And as I said, probably this is what is happening. Maybe the mechanism for neutrino masses, for Majorana neutrino masses, is actually coming from the super high scale. If this is again, I repeat, if this is again the case, we will maybe wait, I don't know, forever to really know what is the original neutrino masses. Then, since we cannot really have access to the super high scale, let's assume just for a second that maybe the B minus cell breaking scale is actually not too far from the electron scale. If this is the case, there is actually hope to test the original neutrino masses at collider, because we can produce the different fields in the theory, and we can look for, in the case of the Majorana case, we can look for lepton violation signatures at collider and test these ideas, okay? The generic idea of looking for lepton violation collider was actually pointed out by Kunas and Janos long time ago in the context of left-right symmetric theories. In that context, generically, you can have extra gauge bosons like WR that can actually allow you to produce, have this channel between sign leptons and jet without any playing with any mixing angle. Generically, you could do that. Of course, assuming that the scale is low. No? In the simplest case, I actually like to discuss because it's a simplest case theory that allows you to produce the right-hand neutrinos at collider. It's just a B minus cell. Here, the right-hand neutrino can be produced through the C prime, the gauge boson associated to B minus cell. The right-hand neutrinos decays to charged leptons and W. If you get the jet from the W, you can actually have very nice signals with sign leptons and jet that allow you to look for lepton violation of collider and try to really test, okay? As I said in the beginning, the minimal gauge theory based on B minus cell doesn't really predict if the neutrinos are Majorana or Dirac fermions, but here I am assuming that this is the case of the Majorana. In the Majorana case, you can actually look for this lepton violation signature and actually try to find to discover the mechanism behind neutrino masses, if of course the scale is low. This is actually a painful issue because since you don't have this, you don't know what is the scale, you have to assume to see if something can be discovered. Okay, then suppose that you want to predict all these signatures with sign leptons and multi-jet, let's say at the Large Hadron Collider. The first things that you have to do is to actually check what are the bounds on the C primes. And this is a plot that is the gauge coupling versus the C prime mass. And you can see now that Atlas is actually doing pretty well already, putting some bounds which are pretty strong for the gauge coupling that you need to compute these cross sections. And of course, the mass of the C prime, okay? And then you can go beyond and compute the cross-section for this process. And you can see that the cross-sections are actually today not so large because the Atlas bounds are actually very, very strong. And you can actually have cross-sections which are actually even below femtobar. Therefore, this automatically tells you that if you want to look for lepton violation using the simple theory for where you can understand Majorana neutrino masses, you will need high luminosity to be able to see something. No? Then, if you want to complete the exercise and actually compute how many events you will get for sign leptons and multi-jet, of course, you will need to compute the branching relations of the right-hand neutrinos to leptons. And there, you realize that you cannot really predict very well because this decay width will depend on the mixing angles that are actually written as a function of the PNMS matrix, the eigenvalues, the line neutrinos, the mass of the right-hand neutrinos, and the so-called R matrix, which is a complex orthogonal matrix that we don't really know. Therefore, you have to assume something for the matrix R to be able to really have a prediction for the branching relation of the right-hand neutrinos and be able to really make a prediction for the number of events. For example, if you just assume that R is the identity matrix, and I'm assuming just the normal ordering here for simplicity, you can actually have a nice prediction for the branching relation of the right-hand neutrinos to leptons in a nice way. However, as I said, we don't really know what is the R matrix. Then if you just consider that it's orthogonal complex matrix and you actually do a scan, you realize that there is no way to distinguish between the flavors, and you have a range of the value of the branching relation can change dramatically once you do the full scan for the R matrix. And therefore, this is what you get, means that it is not a surprise. The theory doesn't predict the M Dirac scale, just only connecting the right-hand neutrino masses to the B minus L spontaneous symmetry breaking scale. And then you can go and consider all the possible value for the R matrix, and that's what you get. That you really cannot make a hard prediction for the Brescian ratio. But this actually something that is actually welcome, because when you try to predict the number of events for these tensile leptons, you realize that, for example, this is the number of events versus the right-handed neutrino mass, just to have an idea how well you can do. And this is the channel where you have electrons and muons in the same sign. And this is taking a low mass value for the C prime, and you're forced to assume a smaller gauge coupling because you want to be in agreement with the Atlas bounds. If you take that the R matrix is identity matrix, you have a well-defined prediction, which tell you that it's actually hard to get too many events in this particular channel. And even if you change the R matrix and you take the most general R matrix and you do the scan, you realize that you can actually increase the number of events, but not too much. And this is even with high luminosity LHC, and clearly this is very pessimistic. However, if you check the channel with two muons, this is the prediction when R is actually the identity matrix. And when R is, you consider the most general R matrix, you actually can increase dramatically the number of events for this particular channel. Therefore, the theory doesn't predict the mixing angles between right-handed and left-handed neutrinos. The theory provides a new mechanism to produce the right-handed neutrino without assuming anything strange about mixing angles. Just a gauge coupling allow you to, in the C prime, allow you to produce the right-handed neutrinos, and changing the most general value for the R matrix and be consistent with the CISO formula, you actually can show that if you have high luminosity, there is actually a hope to see a signature of electron violation at the Large Hadron Collider, which is something very important because the Large Hadron Collider is there. We should do our best, and experimentally should do their best to look for electron violation, because this clearly could clarify, could provide a lot of information about the original neutrino masses. Now, as I said, clearly the bounds, the current bounds for the C primes are very strong. And since here I am talking about the minimal gauge theory that has B minus L, the first thing that you have to do a collider, even before, at the same time looking for the electron violation, violating signatures, is you have to discover the C prime. You have to discover the C prime, measure the couplings to quarks and leptons, and especially to charged leptons and quarks, and establish that this is really a B minus L gauge boson. You can measure the width, and you can do the sensing that we did for the standard model Z to really understand the property of this new gauge boson. This is the way to go. And at the same time, putting everything I mentioned for looking for the production of right-handed neutrinos and the electron violating signatures. Then, however, I show you in the plot that once you start increasing the right-handed neutrino mass, there is a threshold that, yes, the cross-section just goes down dramatically after you basically pass the threshold half of the C prime mass. And in this case, it's actually hard to use to have the direct access to the same sign electron signatures. And then here, what I wanted to mention is that even in this situation, if you discover the B minus L gauge boson and you measure the decay width, you could have some idea of what is happening with the neutrinos, because if I check the Brescian ratio, the invisible Brescian ratio of the C prime to neutrinos, and you are in the regime where basically you have like 23% Brescian ratio for the C prime, this tells you clearly that the right-handed neutrinos are actually massive in the theory, and therefore they should be Majorana, no? And this is easy to understand if you define this quantity here that I call delta gamma nu, that is just basically the difference between the Dirac case and Majorana. And when you have neutrinos at Dirac, clearly you will have the Bragg relation to neutrinos will be way larger. In the case of Majorana, especially if they are heavy, they actually decouple and they don't contribute to the, not decouple, they don't contribute to the decay weight, no? To the invisible one. And then you can do something that is actually nice simultaneously is that if just to understand why this is so important is that if you check the cross section for the production of right-handed neutrinos, clearly you see that the cross section goes down, where this quantity delta gamma neutrino goes up to 1 in the case that when the right-handed neutrinos are heavy. These are two different cases just to illustrate how well you can do, and that is basically what you can do in the simplest gate theories that we have for right-handed neutrino to generate right-handed neutrino masses. Okay, as I said, most of the ideas that we have for physics beyond the standard model, like grand unified theories, clearly they predict that the neutrinos they have to be Majorana fermions. However, it's sad to see that all these ideas they have to realize at the super high scale. Therefore, we never will have access to these scales. And that is why I try to emphasize, to forget about all these ideas and take the simplest gate theory that allow me to understand the spontaneous generation of right-hand neutrino masses to do the job. No? Now, in the rest of the time that I have, let me talk a little bit about the Dirac neutrinos. Yes?
The time is finished. So
okay, I just 2 minutes and I am done. Okay. Then very quick, I only wanted to say, clearly, if the neutrinos are Dirac fermion, which I mean, this is possible, nobody, we don't really know. Clearly, B minus L is conserved. The only thing that we have is this Yukawa coupling to the Higgs. And the fact that, this Yukawa coupling has to be super small will be really, really hard to have access to this because even today, we still don't know what is the coupling of the Higgs to charge to the electron because we don't have enough energy to measure that. Huh? In the case of the neutrino, will be a nightmare scenario, right? Then to finish, I want to say that it's actually possible to write a theory which can actually predict that the neutrinos has to be Dirac fermions, okay? And in this case, the simple idea that we know actually go in detail, but basically, if you take the standard model of particle physics and you ask the question, can you gauge just the total lepton number? You find that there is a simple way to gauge the total lepton number. The total lepton number is not normally free. Therefore, you have to introduce new fermions to cancel all the anomalies. And in this case, when you check the whole theory and you try to generate masses for the new fermions needed for anomaly cancellation, you find something very interesting is that the new fermions must break the symmetry in 3 units. This is actually comma 3. And therefore, this means that lepton number will be broken only in 3 units, and automatically this theory is actually predicting Dirac neutrinos from a spontaneous symmetry breaking. There are many nice things that I cannot mention about these theories, but basically the nice thing about these theories is that automatically one of the fermions that is in the theory is a dark matter candidate. And when you check the phenomenology of this dark matter candidate, which is the leptophilic dark matter, you realize that the scale for the symmetry breaking scale cannot be very large, has to be below like 20 TeV. Therefore, the theory is predicting Dirac neutrinos, is predicting a dark matter candidate from anomaly cancellation, and this implies that the scale for lepton number, spontaneous lepton violation should be below the multi-TeV scale, and therefore there is a hope actually really to see that at collider. Not the Large Hadron Collider is very challenging, but clearly the scale can be very low. And you can ask me how you can actually let's say even test or rule out this particular theory predicting Dirac neutrinos is the fact that the neutrinos are Dirac, they contribute to the N effective, and the bound from N effectives are actually pretty strong. This is around 10 TeV mass for this Z prime. The fact that the next the CMBS4 stage 4 experiment will actually lower the allowed values for N effective, this actually can actually completely rule out this particular theory, which is the minimal gay theory that where you can understand the spontaneous breaking of the local lepton number symmetry in nature, okay? And this is what I wanted actually to discuss today. The first thing is that, let me emphasize, we have a lot of ideas for generating neutrino masses, but we don't really know if it's a Majorana or Dirac fermions. Then the first part, I just try to mention that if we take just the simplest gay theory that we know for Majorana neutrino masses, that is based on B minus L, clearly we can hope to look for lepton relation at the LHC. Of course, there is no even any guarantee. The second part that I wanted to mention that typically people don't really emphasize too much about Dirac neutrinos. I wanted to say, if you want to understand the spontaneous breaking of the local lepton number, the total lepton number, this theory, the minimal one, is actually predicting Dirac neutrino, is predicting a dark matter candidate from anomaly cancellation. Then if you use the cosmological bounds, the scale for this theory has to be actually below the multi-TB scale. Therefore, there is a hope, even if you don't have access to the Yukawa coupling Dirac, there is a hope to really have information about what is the symmetry breaking scale. And the beautiful thing here about cosmology is that the cosmological bounds of the effective number of relativistic degree of freedom can actually play a big role in this case.